Good morning, everybody. So we are going to continue with Bayes' theorem. So just to remind you, the formula for Bayes' theorem is this. Probability of A given that even B has happened is the same as probability of B given that A has happened times the probability of what is given here, probability of A, all of it divided by the probability of what is given here, B. And that's the Bayes theorem. Now, we have used this formula to solve the breast cancer problem. I have spent plenty of time last time on this problem, but I'll just quickly go over that again, even though I did it in multiple formats last time. So let's go ahead and do the problem again. So in a mammogram, mammogram is 90% accurate in correctly predicting breast cancer, okay, in a woman, and 15% inaccurate in predicting it. So 90% accurate in correcting true positive, okay, and 15% inaccurate in predicting false positive. So if you do the table again, someone has cancer versus does not have cancer. Cancer in the population is 1%, is given in the problem, 0.01. Not having cancer chance is 99%. So now you either test positive or negative. This is 0.9. That means you test positive correctly. So incorrectly when you have cancer, but it says that you don't. So that's 0.1. And inaccurate 15% of the times, okay, when false positive. So this is going to be 0.15. And this is going to be 0.85. So when you don't have the cancer, 85% of the times you'll get negative test result, and 15% of the times you'll get positive test result, which is inaccurate. As I said before, these two scenarios, so this one and this one, you want to avoid. Someone has cancer, but it says no, the person doesn't. But on the other hand, someone doesn't have cancer, the test result comes out positive, so it says you have cancer. So these are the two things. So we define two events. C is the event someone has cancer, and positive is the event which is testing positive or tests positive. Okay. As a normal human being, what do? You want to find out what is the probability that you actually have cancer, given that you already tested positive. So probability of having cancer, probability of having C, given that someone has already tested positive. Now, if I use this formula, we are going to have probability of positive, given that someone has cancer, times the probability of cancer, all of it divided by probability of testing positive. Now, probability of testing positive, that requires a little bit of calculation. So probability of testing positive, you can test positive when you have cancer, and you can test positive when you don't have cancer. So these are mutually exclusive. So we'll write probability of testing positive and have cancer plus probability of testing positive and does not have cancer, which, by the way, is going to be probability of cancer times the probability of testing positive given cancer plus probability of not having cancer times the probability of testing positive given that the person does not have cancer. Probability of cancer is 0.01 times probability of testing positive when someone has cancer is 0.9, which is this number. Similarly, probability of not having cancer is 99% times the probability of testing positive when someone does not have cancer is 15%, so 0.15. If you do the math, you are gonna get 0.009 plus 0.99 times 0.15, that is going to be 0.1575, 0.1575. So probability that someone has cancer, given that the person tests positive, is gonna be this. So we are gonna go ahead and plug in this number, which is 0.1575, and then probability of positive given cancer, which is 0.9. If you test, when do you test positive? If you test positive given that you have cancer, so that chance is gonna be 90%, or 0.9 times probability of having cancer is in the population is 0.01, okay? 0.01. If you do the math, it's going to be 0.009 divided by 0.1575. So 0.009 divided by 0.1575, that is going to give you approximately 0.0571, or you have about 5.71% chance that you will have a cancer, given that you randomly select a person off the street or randomly select a person from the population and test. Now, in the second question, I ask you, what is the probability of having cancer given that you test positive twice? Only thing you will do here is that you will replace this 0.01 by 0.0571, okay? And then this number is gonna change too, okay? It's gonna be 100% minus 5.71%, or equivalently 1 minus 0.0571, and it's gonna be 0.9431, I guess, 9429. Check this, I just did it on the fly. Okay, and you can repeat the process. Instead of 2 times, you could do it 3 times. Only thing is gonna happen is this is gonna change. So this is kind of like the gist of what I went over step by step very thoroughly in the last class. Now you should be able to do Bayes' theorem. This is a very exciting formula. Reverend Bayes, who came up with this formula, and it's extremely useful in the real world problems, okay, solving real world problems. So make sure that you have some good sense of this thing. Now I'm going to continue, and this is the last problem that we are going to do from Bayes' theorem, and then we are going to go ahead and move on. All right, so in Bangladesh, a garment factory named Navy Hosiery makes socks at 3 different manufacturing plants named A, B, and C, with 50%, 30%, and 20% of the production coming from them respectively. So A makes 50% of the production, B makes 30% of the production, and C makes 20% of the production. 3 plants. Also, A, B, C have 1, 2, and 3% defect rate. So this one has 1% defect rate. This one has 2% defect rate. And this one has 3% defect rate. Okay. As a quality control manager, you find an item defective. So you randomly select an item is defective. Now you need to analyze and determine the potential source of the defective product. So that means which plant is likely to have made this product. You find a defective product, and the question is, as a manager, you'd like to ask which plant has potentially made this product. Now, in essence, the question comes down to this. So I'm going to quickly remind you this A, B, and C. A is the event that plant A has made the product. B is the event that B has made the product. C is the event that C has made. So A is the event that plant A has made the product. And similarly, B is the event that plant B has made the product. And C is the event that plant C has made the product. And D is the event that a product is defective. D is the event that a product is defective. Now, the question boils down to this. So you have to take the ordinary people's words or sentences and translate that into mathematical expressions. So you take the ordinary people's words. Okay, as a manager, you want to know who made this defective product, and you have to translate it into mathematical equation or formula, and then try to solve the problem. Who made the product, defective product? A made it, B made it, or C made it. So the problem boils down to this. What is the probability that plant A has made the product, given that the product is defective? Because we already know that it is defective because the manager found the product and it is defective. Okay. A, what is the probability that plant A has made the product, given that it's defective? And similarly, we are going to be asking this question. What is the probability that plant B has made the product, given that it is defective? And also we ask the question, what is the probability that plant C has made the product, given that it is defective? Okay. Now, among these three probabilities, whichever is the highest, that's probably the likely plant that has made the product. Okay, so this is sort of mathematical way, or rather probabilistic way of determining who may have produced the defective product. Among these three probabilities, the one with the highest percentage is probably the likely plant that has made the product. So that's where our Bayes theorem comes into play. So probability of A given D is equal to probability of D given A times the probability of A divided by probability of defective. Now we need to find all these numbers. Probability of defective, we don't know, we need to find it. Probability that plant A has made the product, which is easy, 50%. Okay, now what is the probability that A product is defective, given that plant A has made it? That is also given to you. If plant A has made the product, the chances of it being defective is 1% or 0.01. So you have the top two numbers. Now, how about the bottom number? That's when you kind of run into a bit of problem. What is the probability that a product is defective? So you kind of have to think of it a bit logically. If a product is defective, how could that happen? Okay, if a product is defective, How could that happen? What do you guys think?
Somebody made an error. So it could be like a 50-50 chance that you're either going to make it correctly or you're going to make it wrong.
Okay. Good starting point. Anybody else has any other comments?
Maybe a machine error.
Okay. Well, it is. Those are things that's we know that the product is defective. We are not trying to find out what the reason of the defectiveness, but rather we are trying to find out who made the defective product. Is it plant A, plant B, or plant C? So if we want to find out what is the probability of a product, a randomly selected product being defective, how do you go about doing that? That's what I'm asking. How do you find P of D?
Would you have to like maybe do something with like adding all 3 plants?
Who is talking?
Alyssa.
Melissa?
Alyssa.
Alicia? Okay, Alicia, good. I think you are going in the right direction. Anybody else wants to? Because I have done it, by the way. It's the same type of problem as the breast cancer and also the traveling salesman. Okay. Think of it, always try to think like an ordinary person, like how, forget about the math part, okay? Think of it as if somebody off the street thinking or would be thinking. So I got a product and there are 3 plants that make these products. I got a product that's bad. So now, if I want to find out what is the chance or what is the probability that the product is bad, we've got to first ask the question, where is it coming from? It could come from either plant A, or plant B, or plant what? C. It couldn't come from anywhere else, could it? If you have a defective product, it has to come from one of the 3 plants, because those are the only 3 plants that are producing these items. What items? Socks or t-shirt, whatever maybe. So it could be that product is coming from plant A and defective, or it could be that product is coming from plant B and it is defective, or it could be coming from plant C and it is defective. Probability of A or B or C. Now here is a very good time for you to recognize or remember this characteristic of probability. If you have an event A, which is a collection of some events, let's say A1, A2, and A3, and they are mutually exclusive, or they are simple events, okay? They are mutually exclusive and they cannot happen at the same time. So the probability of A is the same as the probability of A1 plus probability of A2 plus probability of A3. That's exactly what the property we are using. If you have a defective product, you cannot have it come from 2 different plants. It cannot be from plant A half the defect and plant B half the defect. That cannot happen. It's a mutually exclusive event. So the problem of finding the probability of defective product boils down to the following: probability of A and D. Probability that plant A has made it and it is defective, plus the probability that plant B has made it and it is defective, plus the probability that plant C has made it and it is defective. So these are the things that you have to kind of think about. Now, probability of defective is going to be probability of plant A. Now remember the order in which you do this that could run into trouble, but we are gonna go ahead and keep going. I have talked about it at least 3-4 times before. If you try to write it as probability of defective times the probability of A making it given defective, you'll run into problems. So you don't want to use that version, okay? You don't want to use it. You want to use this one, probability of plant A making it times the probability of defective given that A has made it. Similarly, probability of B making it times the probability of defective given that B has made it, plus the probability of C making it times the probability of defective given that C has made it. Now, probability of defective is going to be what is the probability that A has made it, which is 50% or 0.5. What are the chances that it will be defective? They give you 50% and 1% or 0.01. Similarly, for B, 30% and 2%. So it's going to be 0.30 times 0.02. Similarly, for C, 20% and 3%. 0.20 times 0.03. If you do the math, you'll get probability of defective is going to be, oh, you can see it on the screen, it looks like. So if you do the math, probability of defective is going to be so I'm just going to do the whole thing on the calculator. 0.5 times 0.01 plus 2 times 0.02 times 0.3. So that's going to be 0.017. So the probability that an item is defective is 0.017. Can somebody quickly also check the calculation? I did it quickly. So let me just double check. 0.03 times 0.2 plus 0.3 times 0.02 plus 0.5 times 0.01. Yes, it is 0.017. So this number is 0.017. So look. Now, if you do the math, 0.01 times 0.5 divided by 0.017, that gives you 0.2941. So this is 0.2941. So there is 29.41% chance that plant A has made it. Okay, there is 21.41% chance that plant A has made it. Now, similarly, you do the other calculations, okay? So probability of defective given that B has made it, okay, is gonna be, let me clean up the screen so that, remember this number, probability of defective is 0.017. Probability of defective is 0.017. So what is the probability of defective product given that B has made it, which is gonna be probability of B given defective times the, oh gosh, hold on, let me just clean it up. Probability of defective is 0.017. So what is the probability that plant B has made it given that it is defective? That's what I'm looking for. So it is going to be probability of defective given that B has made it times the probability of B, all of it divided by probability of defective. Now, if you do the math, it's going to be 0.017 in the bottom. On the top, the probability of a defective product from B is 2% or 0.02. And B makes 30% of the product, so 0.30. If you do this math, so 0.02 times 0.3 divided by 0.017 is going to give you 0.3529. 0.3529, or approximately 35.29% chance. Now, similarly, the product is defective given what are the chances that C has made it. So probability of C given D is gonna be probability of D in the bottom, then probability of D given C times the probability of C, and that is gonna be 0.017 in the bottom, and on the top, there's a 3% chance that if C makes it is defective, and there's a 20% chance that the product is made at C. And if you do the math, it is gonna be also 0.3529, or approximately 35.29% chance. So for the A, the probability was approximately 29.41%. So for A, about 29.41% chance that it made the defective product. For B is 35.29%, and for C is 35.29%. So that's what it is. So probably the product came from either B or C. That's what our best guess. Okay. So that's how you'll do these problems. So I have given you sufficient examples of Bayes' theorem, and it is a bit of a hard concept. It takes a little bit of time and thinking. So if you are not following it, I would recommend watching the video a few times and asking me questions in the class and whatnot. Okay, make sure that you try it first on your own and then ask me questions, okay? And watch the video a couple of times. It'll start to make sense. Okay, folks, that's all for Bayes' theorem, and let's move on. But before I move on, any questions, anybody? No questions? Everybody okay? Everybody's all right? No questions? Everything okay?
No question.
Everything's good.
Oh, that's surprising. I was expecting that you'll have questions. Everybody is okay. That easily you got the concept. That's nice. And just a reminder, midterm is on March 3rd. Once again, I announced it, March 3rd, that's a Wednesday. Wednesday, March 3rd, I'm gonna open the midterm at 6 a.m. and it will be available until 11:59 p.m. So you have about 18 hours to work on it, and you can work on it as frequently as you want. You can work on a problem and go and have coffee and come back and work on another problem. You can submit it as many times as you want within the window of time. So everything is the same. The only difference is that only difference between homework and the midterm is that in the homework, sometimes you have step-by-step or videos or whatnot, but in the midterm, you will not have any of those. You'll have just the question and the answer box, and you do your work on a piece of paper, and then put your final answer on the inside the box and check your answer. As you take the test, you'll see your score. It'll get updated live in the corner. So you can see whether you're doing well or not. It is a live update, okay? Okay, so let's move on. Next topic is gonna be, now things are gonna get a little easier. I think, in my opinion, the most difficult part of the class is over, which is the Bayes theorem. That's kind of, in my opinion, the most difficult part. And then there is one more difficult part. That one is central limit theorem, okay? But that one is slightly easier than Bayes theorem to understand, because Bayes theorem formulation of the problem and applying it into the real world scenario is difficult. So one more thing that you might run into a bit of a problem is the sampling distribution and the central limit theorem. And other than that, everything should be pretty routine and straightforward. If you just chug along and you know, keep up with the materials, do the homework online, you have no problem. All right. Counting rule. So fundamental counting principle. What is it? If you have an event A, okay, so you have an event A, another event B. If event A can happen in M different ways, event B can happen in N different ways, they are independent events. They don't influence each other. If event A can happen in M different ways and B can happen in N different ways, together they can happen in M times N different ways. Let's say Adam and Brittany. Adam can dress in, wear two different t-shirts. He can dress in two different ways, and Brittany can dress in three different ways. Okay, let's say wear three different t-shirts. Together they can dress in 2 times 3 or 6 different ways. Adam can dress in 2 different ways and Brittany can dress in 3 different ways. Together they can dress in 2 times 3 or 6 different ways. Here is an example. Let's say Adam has a blue t-shirt and a black t-shirt, and Brittany has a pink t-shirt, yellow t-shirt, and a green t-shirt. Okay, so think of it this way. If Adam wears blue t-shirt, Brittany can wear either pink or yellow or green. So in essence, this becomes B and P, B and Y, and B and G. So three here. Now, on the other hand, if Adam wears a black t-shirt, Brittany can wear pink, she can wear yellow, and she can wear green. So then it becomes black and purple, black and pink, and then black and yellow, and black and green. So you can see there are 6 different possible combinations or 6 different ways this could happen. So Adam can dress in 2 different ways, Brittany can dress in 3 different ways. Together they can dress in 2 times 3 or 6 different ways. I just gave you a very simple example. Now, this can be extended to any number, by the way. It doesn't have to be 2. Now, let's say you have 3 different events, A, B, and C. This can happen in M different ways. This can happen in N different ways. This can happen in P different ways. Together, then they can happen in M times N times P or M and P different ways. And who said that it has to be 3, you could arbitrarily extend it to any fixed number, okay? So it could be 4, 5, 6, 7, 8, 9, 10 different events. But for the most part, we will stick to 2 different ways, okay? 2 different possibilities. But it could be extended to n different ways. Any questions, anybody, about fundamental counting principle? Any question? Okay.
No.
Now let's introduce a concept called factorial. Here is an example. 1 with an exclamation sign. 1 with an exclamation sign. We call it 1. 2 with an exclamation sign. There's going to be 1 times 2 is equal to 2. 3 with an exclamation sign is going to be 1 times 2 times 3, or 6. 4 with an exclamation sign is read factorial. 1 times 2, 2 times 3 times 4, or 24. 5 with an exclamation sign is going to be 1 times 2 times 3 times 4 times 5, or 120. 6 with an exclamation sign is going to be 1 times 2 times 3 times 5 times 6, or 720. And in general, any positive integer n with a factorial is 1 times 2 times 3 times n minus 1 times n. That means you multiply all the numbers starting from 1 up to that number n. You multiply all the numbers starting from 1 up to that number. Now, this is called factorial of an integer, positive integer. There is only one interesting scenario that I want to bring to your attention. I'm going to write it here. 0 factorial, we always define it to be 1. Remember this special value. And factorial is not defined for negative numbers or fractional numbers. You cannot define factorial for 1.2. That doesn't work. Okay, you cannot define factorial for negative 5. It's only for 0 and positive numbers, which is basically whole numbers. Whole numbers include 0, I think, right? 0, 1, 2, 3, 4, 5, 6. So factorial is defined for 0 or positive integers. Now, if I were to do something, so I'm going to give you some examples here right now that's going to help you do some of the problems. So if I gave you 7, let's say 7 factorial divided by 3 factorial times 4 factorials, how do you simplify it? This is what you want to do. 7 factorial, you could write it as 7 times 6 times 5 times 4 times 3 times 2 times 1. But I'm not going to write 4 times 3 times 2 times 1, but it is 4 factorial. So this is one critical step that you should know. 7 factorial is 7 times 6 times 5 times 4 factorial. And in the bottom, why did I go to 4 factorial? Because there is a 4 factorial in the bottom. So 4 factorial, so that they cancel. Then 3 factorial, I could write it as 3 times 2 times 1. Now, this 4 factorial and 4 factorial cancel out. 2 goes into 6 3 times, 3 goes into 3 once. So you're left with 7 times 5, or 35. On the other hand, if you see something like 12 factorial divided by 3 factorial times 4 factorials, this is what you don't want to do. Okay, people who do something like this. 3 goes into 12 4 times, 4 cancel out, it's 1. That is incorrect. That's a very common mistake that students make. You cannot cancel the factorials. You cannot cancel the factorials until you simplify them, until you break them down. So that is one of the things that you want to keep in mind. You need to be able to break it down first. So the way I did the cancellation here is incorrect. Please don't do that. To simplify, 12 factorial divided by 3 factorial times 4 factorial is going to be, you have to break it down. 12 times 11 times all the way down to 5 times, then 4 factorial, right? Then 4 factorial here in the bottom, then 3 factorial, you still have to simplify. 3 times 2 times 1. 3 times 2 is 6. There is a 6 here. So 6 and these two are going to cancel out. So your answer is going to be 12 times 11 times 10 times 9 times 8 times 7 times 6 got canceled, 5. And whatever number comes out, that is your answer. However, if you do it this way, this is completely wrong. Please don't do it. It is wrong. And it's a very typical mistake that students make. This is called factorial. So this is a mini thing on factorial, and you should be able to do these problems. So let me give you a couple other examples of manipulating factorial. So let's say 14 factorial divided by 7 factorial times 8 factorial. All right, I just made it up. So let's see if it comes, what does it come out to? 14 factorial, I'm gonna write down 14 times 13 times 12 times 11 times 10 times 9 times 8 factorial, right? And then 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, then times 8 factorial. Now look, 8 factorial and 8 factorial is going to cancel out. Then let's see. 7 and 2, 14, and this 14 is going to cancel out. 6 goes into 12 2 times. Okay. 2 goes into 4, 2 goes into 4 twice. 2 goes into 10 5 times. 5 and 5 cancel out. 3 goes into 9 3 times. So everything in the bottom is gone. Normally, that's how you get it. And on the top, you're going to get 13 times, so this number times 11 times, what else is left? 3. So it's 33 times 13. 33 times 13 is 429. So that's what it is. You'd need to simplify it and then do cancellation. Do you guys feel that you are okay with these examples? You can handle this, or you want me to do 1 or 2 more examples? Everybody okay?
Could you do another one, please?
Okay, so let's try it. Another one. So let's do 20 factorial divided by 16 factorial times 4 factorial. Okay. So 20 factorial, I could write it as 20 times 19 times 18 times 17 times 16 factorial. All of it divided by 16 factorial. So keep in mind, whatever is the highest factorial in the bottom, that's how far you want to go. Okay. Whatever is the highest factorial in the bottom, that's how far you want to go. And then the other one, you just have to simplify. 4 factorial is 4 times 3 times 2 times 1. Now, in terms of cancellation, 16 factorial and 16 factorial is going to cancel out. Then let's see. 4 goes into 20 5 times. 2 goes into 18 9 times. 3 goes into 9 3 times. So your final answer should be 5 times 19 times 3 times 17. And if you multiply it out, you should get 5 times 19 times 3 times 17. It is 48, 45. And that's what you will get. Okay. Is it all right, everybody?
Yes.
All right. I'll
Yes.
keep. Thank you. I'll keep moving. These things is going to start to make sense, more sense, once I start doing actual problems. So let's do some problems. So this is the application of fundamental counting principle. You have an access code with 6 characters. First 4 are digits. Digits means 0, 1, 2, 3, all the way up to 9. First 4 are digits and the last 2 are alphabets, which are case sensitive. Alphabet means A, B, all the way up to Z, right? Now, case sensitive means you have to remember it could be A as well as B and all the way up to what? Z. Now, a thief trying to break this code has the probability of success. Okay, so if there is a thief out there who is trying to break your account, your particular account, what are the chances that he or she would be successful? You can think of this as 6 different events: A1, A2, A3, A4, A5, and A6. You can think of this as 6 different events. So now, how many different ways event A is? Maybe I should write it here. A1, A2, A3, A4, A5, and A6, 6 different events. So the first 4 are gonna be selecting a digit. The last 2 are gonna be selecting an alphabet. So what is the probability that, how many different ways event A1 can happen? That means how many different ways you can pick a digit. There are 10 digits in the number system, so 10 different ways this could happen. Now, how many different ways event A2 can happen? That's also 10 different ways, because they do not tell you that you cannot repeat a digit. So it has to be 10 different ways. So now event A1 can happen in 10 different ways. Event A2 can happen in 10 different ways. Together, they can happen in 10 times 10 or 100 different ways. Now, how many different ways event A3 can happen? Also 10 different ways. So it's going to be 100 times 10, which is 1,000. How many different ways event A4 can happen? It's going to be 1,000 times 10, because A4, you can still pick one of the 10 digits. So that many ways. Now, how many different ways event A5 can happen? That means you select an alphabet, which is, by the way, 26 for lowercase, 26 for uppercase. So 26 plus 26 is 52 different ways. How many different ways event A6 can happen? Also 52 different ways. Together, how many different ways they can happen? This many ways. Now, this is the number of ways you can select the digits. This is the number of ways you can select the alphabets. Together, how many different ways can you do that? You just multiply this with that. And if you do this, you're gonna get this number. Okay? If you do that, you're gonna get that number, which is 1 out of 2. This is even off, by the way. This is 270400000. So there should be about 1 in 27 million. So this should be right here. About 1 in 27 million chances. So I think you're better off doing something else. But in reality, it's not that simple. This is a very abstract example. In reality, people, those who those who are trying to break into the accounts, they have sophisticated programs, or they have a lot of algorithms that they follow. So, but this is just a very simplified example. If somebody without any knowledge of this, how this password system works and whatnot, just randomly trying to figure out, hey, I want to get into this account, then this is the probability that he or she would get into the account. So extremely low. Any question on this one before I move on? Next one. Again, it's pretty simple. You have the option of buying one car from 5 different types, and you may pick one insurance from 4 different choices. Together, how many combinations or how many different ways can this happen? Which is 5 times 4, which is 20 different ways. Very simple. Fundamental counting principle. Now, let's talk about permutation and combination. I like to start this with an example. So let's take the background off. So we're going to talk about permutation. And combination. Permutation and combination. So think of 3 different colors, R, G, B, red, green, and blue. You have 3 different colors, red, green, and blue. From this, you're going to pick 2 colors. Pick 2 colors. You could pick where order matters. So pick 2 colors, okay, where order matters. So you could pick red and green, or green and red, because order matters, so they are not the same. You could pick green and blue, or blue and green, or you could pick blue and red, or red and blue. These are all the different ways you can pick. So if you pick 2 colors from a group of 3 distinct colors, If you pick 2 colors from a group of 3 distinct colors, the number of ways you can do is 6. You can see red, green, green, red, green, blue, blue, green, blue, red, red, blue. 6 different ways. When you are selecting 2 items from a group of 3 items, distinct 3 items, where order matters, what you are doing is permutation. Very important, order matters. Okay, you are doing permutation. So permutation of 2 items from a group of 3 items. Permutation of 2 items from a group of 3 items. So that's permutation. Now, in general, instead of 3 items, if you have n items, okay, if you have n items, n distinct items, if you have n distinct items, what happens? Now, from n distinct items, let's say you pick r distinct items, r items. If n of them are distinct, then of course, if you pick r of them, all of them are going to be distinct. So you pick r items where order matters. Then what you are doing a permutation of r items from n different items. So we write it in this notation, n, p, r, and that number, here I gave you with an example, there is a way to derive it, and you can actually play around with it, and you will see if you do spend sufficient amount of time and play around with 4 or 5 or 6, you will see that permutation of r items from n distinct items is nothing but n factorial divided by n minus r factorial. Okay, n factorial divided by n minus r factorial. That's what it is. And there is a logical way of deriving it, so which I could do, but I think at this early stage, giving that information would more confuse you than anything else. But for now, just take this thing, okay? Take this as a formula for permutation. The key thing about permutation is order matters. On the other hand, what happens if the order doesn't matter? Okay. On the other hand, what happens if the order does not matter? Okay, can you guys hear me?
Yes.
My screen just froze. Not a good sign. Oh, thank God. Oh no, my pencil froze, maybe. Let me see. Okay, good. Maybe my pencil. Give me a second, okay? So now think of this scenario. So here we have considered a situation where you're permuting r objects from n distinct objects where order matters, right? Permutation implicitly it means order matters. Then this is the formula. But what if you have a different scenario where order does not matter? Okay, what if order does not matter? Everything is the same, but order does not matter. Then what you are doing is called combination. In that case, what's going to happen if order doesn't matter? R and G and R is the same as R and G, okay? Because order does not matter. G and B is the same as the B and G, or G and B, whatever way you put it. B and R is the same as the R and B, or R and B. So now it comes down to what? 3 different ways. If order does not matter, then you can take 2 items, or you can select 2 items from a list of 3 distinct items is in 3 different ways. And the formula for that is n distinct items. You do a combination of R distinct items, or R items from n distinct items. And that formula is n factorial divided by n minus R factorial times R factorial. And I have put the formulas side by side so that you can do a comparison. Only difference between these 2 formulas is that combination has this extra R factorial in the bottom. Otherwise, it's the same. Combination has extra factorial at the bottom. Otherwise, it is the same. Now, key thing to remember, permutation order matters. Combination order does not matter. Permutation order matters. Combination order does not matter. This is very important. So when you're going to be solving problems, you should be thinking whether order matters in the context of that problem, or the order does not matter. Okay? Whether the order matters in the context of the problem or it doesn't. Any question, anybody so far on the permutation and combination? Okay. You can read it up here. Sometimes permutation is denoted this way, the formula, but no worries. Just stick to what I'm doing, that's okay. But if you see this notation, don't be surprised. That's what it means, permutation. And this formula, this is another version of the formula. I probably won't go over that. Okay, so just use this guy. Okay, now let's go ahead and do a few problems. I kind of want to do a very simple problem first. Let's see. Think that you have 8 different chairs. Chair 1, chair 2, chair 3, chair 4, chair 5, chair 6, chair 7, and chair 8. And you also have 8 people. You have 8 different chairs and 8 different people. You want to place 8 people in 8 chairs, okay? If order doesn't matter, so first scenario, order does not matter. That means you're doing combination. Remember, if order does not matter, you're doing combination. Combination of 8 items from 8 items, okay? Or you're selecting 8 people from a group of 8 people. So order doesn't matter. How many ways can you accomplish this? Can you help me out? How many ways can you accomplish this. Anybody, any question? Okay, nobody has any comment on this? No one? All right. First of all, order doesn't matter. So it really is, in essence, one way you can accomplish this. 8 people picking 8 chairs, order doesn't matter. So there is only one way they can sit. However, if order matters, then what happens? In that case, you're doing permutation. In that case, you're doing permutation. So the first chair could be occupied in how many different ways if there are 8 people? 8 different ways this can happen. Now, this is an event. You can think of it as an event, something happening. First chair could be occupied by people in 8 different ways because there are 8 people. Now that you have one person occupied the first chair, how many different ways the second chair can be occupied? Now I need a volunteer. How many different ways the second chair can be occupied? Anybody?
Would it be 8?
Okay, good. But any other suggestions, anybody? Okay. Actually, it is not 8. Just because one person has already occupied the chair 1, how many people are left? There are 7 left, right? So 7 different ways. Chair 2 could be occupied. Then together, they could be occupied in 7 times 8. Now that the second chair has been occupied, how many people are left to occupy the third chair? 6, right? So together, these events can happen 8 times 7 times 6. Now that third chair has been occupied, how many people are left for the fourth chair? 5.
5.
So this could be happening. So these are events you can think of, separate events, and together they can happen this many ways. How many left for this one? 4. How many left for this one? 3. How many left for this one? 2. How many left for this one? 1. Oh, by the way, if you look at this should ring a bell. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is nothing but what? 8 factorial. So 8 people can occupy 8 chairs where order matters in 8 factorial ways. Now I'm gonna come up with the same number, but using the formula. And also I'll do the same thing for here. For combination, where order doesn't matter, there is only one way of doing it. So remember, permutation formula, NPR is equal to n factorial divided by n minus r factorial. Now my n, by the way, here is 8 because there are 8 people, and r also is 8 because from 8 people I'm selecting 8 people. Then this formula becomes 8 factorial divided by n is 8 minus r is 8, 8 minus 8 factorial 8 factorial divided by 8 minus 8 is 0, or 0 factorial. Now remember, I told you what is 0 factorial is?
1.
1. So 8 factorial divided by 1 is 8 factorial. See, that's exactly the same number that we got, but in different ways, using different logic. This is more logical thinking, or analyzing the problem and coming up with this number, and this is using the formula. Now let's do the same thing, but this time we are going to do combination. So it's going to be NCR is equal to n factorial divided by n minus r factorial times r factorial. Now, what is my r, n, and r here? Again, I'm picking, considering 8 people, and from that I'm picking also 8 people where order does not matter. Order does not matter. So pay attention. Okay, so now I'm going to plug in the numbers. N is 8 factorial divided by n minus r, 8 minus 8 factorial times r is 8, or 8 factorial, which is going to give you 8 factorial divided by 8 minus 8 is 0, 0 factorial times 8 factorial. So 8 factorial and 8 factorial cancel out. That gives you 1 over 0 factorial. But 0 factorial is 1. So 1 over 1, or 1. See, they're the same numbers. Okay, you came up with the same answer in two different ways. One is by thinking about the problem and analyzing the problem, and another is by applying the formula. Any question, anybody? No questions? Okay. So let's move on. Okay, so here is a problem maybe we could work on. So I'm working on this problem. A student committee consists of 13 members. They need to elect a president, a vice president, and a treasurer. How many different ways can this be accomplished? Now, you have 13 people. The committee has, you have to pick 3 people. Out of those 13 people, one is going to be a president, another is going to be a vice president, another is going to be a treasurer. The question is, how many different ways can this be accomplished? Now, here is the interesting part. Before you do the problem, you should be asking, I'm selecting 3 people out of 13. Does order matter or it doesn't matter? What do you think? Does order matter or it doesn't matter? Okay, here the order does matter, by the way. Now, order does matter because let's say John becomes the president, okay? Then Jennifer becomes the vice president. And Jamie becomes the treasurer. If you change the order, I think it's not the same thing, right? So order matters. If you are doing order situation, we are selecting 3 items or 3 individuals, in this case, out of 13 individuals, where order matters, you're going to do permutation. So which is going to be 13 factorial over 13 minus 3 factorial, which is 13 factorial is just 13 factorial. 13 minus 3 is 10 factorial. Now we could write it as 13 times 12 times 11 times 10 factorial divided by 10 factorial. This 10 factorial cancel out. That gives you 17, 16 if you multiply 12, 11, and 13. So that many different ways you can do it. Now I'll leave it up to you for you to try at home. There is really not much. It's the exact same problem. I just changed the number. 15 members. You need to elect president, vice president, and treasurer. So your answer should be 15 P3. So it's going to be 15 factorial divided by 15 minus 3 factorial. 15 factorial divided by 15 minus 3 is 12 factorial. So 15 times 14 times 13 times 12 factorial divided by 12 factorial. These cancel out, and whatever number comes out when you multiply this. 15 times 14 times 13. Okay. All right, so this is a problem I kind of like. Next one. So it's all about permutation, combination, and then fundamental counting principle and those applications basically. So there are a couple of problems here. So let's go ahead and do all of them. Okay. Then we'll be done with permutation and combination. Let's see how much time we've got. We've got a little bit of time, so we can do these problems. So what are your chances of winning the Mega Millions lottery? Okay, so Mega Millions, you hear about it, and what are your chances of winning the Mega Millions? In Mega Millions, what do? You select 5 numbers. 5 numbers from 1 through 56. 1, 2, all the way up to 56. Those are the regular 5 numbers. And you select one number from 1, select. Then select one number from 1, 2, all the way up to 46. All right, so let's take the background off. So you select 5 numbers from a list of 56 numbers, 1 through 56, and you select one number from a list of 46, which is called the mega number. So if you match the mega number as well as the 5 different numbers, okay? If you match the mega numbers and the 5 different numbers, then you will be winning the lottery. All right, you will be winning the lottery. Now you can think of these, by the way, as 2 different events. Okay, you can think of this as 2 different events. So let's go ahead and do it. So the first one is selecting the five numbers. So event A is selecting the 5 numbers. Event B is selecting the mega. Now, Here is a question again I would like to ask. You are selecting 5 numbers for a lottery. Does order matter or it doesn't? That's the question I would like to ask to everybody. Does order matter here?
Yes, order matters.
Order matters. Okay. Who is talking? Alicia
Jerry.
or Jerry? Okay. Order matters. Okay. Anybody else? Edgar, does order matter or it doesn't? Do you guys play the lottery, first of all?
I don't think the order matters.
Who is talking?
This is Eric.
Eric thinks order doesn't matter. So think of, lottery. Sometimes you buy scratchers, right? You have to match 3 numbers and then you win. When you buy scratchers and you have to match 3 numbers, then you will win. Do you have to have the numbers in certain order to win, or you just match them?
You just
I
have
believe
to have a
it's
match.
You just have to have a match. That's exactly what it is. Let's say the winning numbers are 5, 17, and 19. Okay, for a scratcher, winning numbers are 5, 17, and 19. Okay, so if you match them, you will win, but it doesn't matter in what order you are matching them. It really doesn't matter in what order you are matching them. If you match 19 first and then 5 and then 17 versus 17 first, 9 and 5 and then 19, it really doesn't matter. So order does not matter. If order doesn't matter, what are we dealing with? We are dealing with permutation or combination. If order doesn't matter, are we dealing with permutation or combination? Someone said something. It is combination, right? If order does not matter, then we are dealing with combination. So the problem boils down to this. You have a list of 56 items. So that means your N is 56. And from 56 items, you're selecting 5 items. That means your R is 5. So the number of ways event A can happen is 56C, 5 different ways. Okay? Because order doesn't matter. And then the number of ways you can select a mega. In this case, if you're selecting one item, it really doesn't matter. Order doesn't matter. If you select one item, order doesn't matter. So it's still a combination. But in this case, your N is 46, your R is 1. So it's going to be 46C1. So event A can happen in this many ways. Event B can happen in this many ways. Fundamental counting principle. Together, they can happen in this many ways. This times this many ways. Now you have to do the calculation. So I'm actually going to do the calculation here so that you guys get a feel for it. So let me just try to do it here. 56C5, which is going to be 56 factorial divided by 56 minus 5 factorial times 5 factorial. That is going to be 56 times 55 times 54 times 53 times 52 times 51. Oops. 51 factorial. Now, why did I go down to 51? Because 56 minus 5 is 51. So 51 factorial times 5 factorial is 5 times 4 times 3 times 2 times 1. Now things are going to cancel out. 51 factorial is going to cancel out. Then let's see, there is something easy to cancel out here. Okay, 5 goes into 55 11 times. Okay, 4 goes into 56 14 times. 2 goes into 14 7 times. 3 goes into 54 18 times. So everything is cancelled out in the bottom. So on the top you have 7, 11, 18. So 7 times 11 times 18 times 53 and 52. 53 times 52. And if you do this calculation, I think you're gonna get, what number will you get? You'll get this number, 3819816. 3819816. So this is gonna be 3819816. So this is 3819, 816. So this event can happen in this many ways. Now, how about the other one, 46C1, which is very easy, just 46. So 46 factorial divided by 46 minus 1 factorial times 1 factorial. So 46 factorial is 46 times 45 factorial divided by 46 minus 1 is 45 factorial times 1 factorial is just 1. This cancel out, that gives you 46. So this event can happen in 46 different ways. Together, how many different ways they can happen? This number multiplied by this number, and that will give you this number. Let me look it up. What number is it? 175, 711, 536. 175, 711, 536. 175, 711, 536. So that means that many ways you can actually buy the lottery tickets for Mega Millions. 175,711,536 different ways. Okay. 175,711,536 different ways you can buy the Mega Millions lottery. So let me just show it in red. That many ways, or that many possible tickets that you could buy from Mega Million as an individual. Now, what are your chances of winning the Mega Millions? There is only one of these combinations. So these many combinations are possible. 175,711,536 combinations possible. Out of that, there is only one winning number. So your chances of winning the Mega Millions lottery is 1 out of 175,711,536. So your chances of winning the Mega Millions is roughly about 1 in 175 millions. Okay, roughly. Or you can say even 176 million. So that's a pretty low probability of winning, 1 in 175 million. You have more chances of getting struck by the lightning, and you have a much higher chance of getting in a car accident. You have much higher chance of, winning lotteries in Vegas. I mean, slot machine and all those things. So the question comes down to this. This is a small probability. So maybe it's not a good idea to play lottery as much. Yet many people do play. And here is one thing I kind of want to talk about that's kind of interesting. I do talk about it with my students all the time. Even as recent as within the last couple of months, maybe within the last month, Mega Millions, okay? Mega Millions lottery, it went up to, I think, like $1 billion or close to 1 billion. Yeah, I think 1 billion. Mega Millions has gone up to 1 billion. And I think right now Mega Millions is like $2 or something. You pay $2 to buy the tickets. So let's say this number is 176 million to make things easier for you, okay? So if you multiply this by $2, because each ticket is $2, that comes out to 253, okay? So it comes out to $352 million, okay? So what do? You go to your local or Bank of America or Chase or Wells Fargo, big banks or some other bank. You go there and say them, hey, can I borrow $352 million from you today? Okay. And in 2 days, when you win the lottery, because you're gonna win $1 billion, and you're gonna give them back 350 instead of 352 millions, in a week or in a couple of days, after you win, you give them $360 million. Okay, in 1 week, let's say you give them $360 million. They just made $8 million profit. They would be like so happy with you that they'll probably fly you around the world on private jet. They wouldn't think about it twice if you wanted that, because it's not going to cost you $8 million to go around the world on a private plane. It's not even going to cost you 1 million. So these banks would be treating you, wining and dining you, and treat you like royalty because you're giving them so much money. Because you're going to get 1 billion, why not just give 360 million? 1 billion is, by the way, 1,000 million, so that you know. 1 million is 1,000, 1 billion is 1,000 million. So it's like you have $1,000 million and you just give away 360. You still have $640 million left. You should be instant rich. However, how come people are not doing it? It is true. What I'm just saying is absolutely true. You could buy all the lottery tickets at $2 a piece. And if you buy 175,711,536 lottery tickets, is going to cost you roughly about $352 million or slightly less. And you are guaranteed to win. If you buy out all these tickets, there is no way you're not gonna win. You will be winning for sure. You will be winning the amount. So 1 billion, or easily Mega Millions go up to $500 million. Easily 400 or 500 millions. Why not buy out all the tickets for 500 millions? And win the $500 million and give them 360. You still have a lot left. Well, how about, even if I have $1 million for sure, I'll do it. If I have $1 million for sure, I'll do it. But how come people are not doing it? What do you think? Don't think people don't know about it. Your teacher doesn't have any magic that other people don't know. If I had some magic like this, I'd be very happy. I'd be teaching probably for fun, which I do still for fun, but I get paid too. Then if I can win something like this, I'll be doing it for free, for humanity, okay? Helping out people. How come people are not doing it? What do you think? Anybody?
Is it because somebody else could get the exact same combination also, and then you guys would have to split the winnings, right? I think.
Yeah, you're absolutely right. There is one consideration. Somebody else could win it. Even after that, many times not multiple people are winning. Let's say so multiple winners. One is multiple winners. Okay. But in reality, many times there is just only one winner. Okay, not multiple winners. There are times when there is just one winner. So other than that, let's say hypothetically speaking, you are the only winner. Even after that, you shouldn't be doing it, or you couldn't do it. Why? Anybody? Nobody? Okay. So here is the thing, taxes. You have to pay taxes, which is almost 50%, right? Let's say you win $1 billion, they're gonna charge you taxes on it. Let's say 40%, let's say, okay? 40% tax. So you still have $600 million left, which is still good. But then again, $600 million, you cannot just go and say, hey, give me 600 million. What they're gonna do, you are supposed to get this $600 million over 20 years. Did you know that? However, there is an option, okay? There is an option where you will be getting this $600 million, I mean, present value of $600 million cash flow over 20 years. That means instead of getting, let's say 1/20th of or 30 million each year, okay? So you're gonna get in year 1, 30 million, year 2, 30 million, year 3, 30 million. And after 20th year, you'll be getting actually $600 million. But then what happens? You have to give the bank money. Bank is not gonna wait for 20 years, okay? Then these cash flows over 20 years is discounted. There is a concept called discounting. It's discounted to the present value, discounted to present value. What is the present value of 600 million cash flow over 20 years? If you do the present value calculation of this cash flow, and I'm very sure they use pretty high interest rate, okay, you will not even get 300 million. You borrowed 360, now you are at 300. Does it work? Now, what if there are two winners? Then you don't even get 300, you probably get 150. Okay, so does it work? So that's the reason. These are the reasons that people do not buy lottery tickets. Otherwise, people would buy like crazy and win it. Okay. There will be people who will take risk, and you don't even have to take risk. Okay. What you do, you get 175 million people together. Hey, you know, we will spend $360 million, or get a bunch of people together and spend $360 million. You don't even have to go to the bank and then win the lottery and take the difference and divide it among yourselves. And that's exactly what I heard that a mathematician was doing in Paris many years ago. In Paris, they used to have apparently a lottery where you didn't have to pay taxes or anything. You just wait and get the money. And that mathematician, he figured it out. Hey, if I can get a bunch of friends together to contribute to buy all the lottery tickets. So he got a bunch of people together, a bunch of his friends, and they put money together so that they could buy out all the tickets. And once they bought all the tickets, obviously they won, and then they distributed the winning among themselves after paying off the main investment. And they have kept winning. And after a while, I think, or I heard, if this story is true, the lottery issuers, they figured it out. Hey, how come people are winning all the time? and they're losing money, I guess. Then they stopped and changed the rule or something like that. So interesting. So Mega Millions, yes. So this is how you should be thinking. Your chances of winning the Mega Millions, if anybody asks you, it's about 1 in 175 or 176 million. Okay. Your chances of winning the Mega Millions is 1 out of 175 millions. You have many other chances, many other higher probabilities of bad things happening to you. Okay, I told you, getting hit by lightning or getting in a car accident, or I don't know. All right, so now while I'm on the topic, I kind of want to talk about another very interesting thing, which is this. Winning the Mega Millions in and of itself, it's a rare event. Okay, it's an outlier. A rare event is an event that is extremely unlikely to happen. Okay, it's an extreme outlier. Rare events, it depends how people define. Some people define rare event as being among the top 5% or bottom 5%, but I'm talking about not 5%. I'm talking about way smaller than that. So this is extremely small. Now, what are the chances that a person would win the Mega Millions twice in a row or 3 times in a row? That could, in theory, happen. If an individual plays 3 times in a row, wins the Mega Millions 3 times. But in theory, it is possible, but in reality, it has never happened and very unlikely to happen. So this is an extreme outlier. Remember the definition of outlier? An outlier is a number or an event that is very less likely to happen. It's not common, okay? And we defined it as being beyond 2 standard deviations, right? But here I'm talking about an outlier that cannot happen. You know, it's not beyond 2 standard deviations. It's probably beyond 20 standard deviations or even more, who knows? All right, I think we did talk about a lot of stuff about permutation, combination, and lotteries. Let's clean up the screen. And now that I have done this problem, you should be able to do the next problem, this permutation combination problem here. So that's the lesson. Sorry, I'm talking about the problem here. And next problem is here, which I have done it here, but I kind of want to talk about it, and let me just finish up this section. So 13 managers in a company, they laid off the 3 managers with the highest salaries. Was there discrimination involved? So times are tough, like right now. So a company is struggling. They have 13 managers. They laid off 3 managers who happen to earn the most in the company, let's say. So now they are saying they are being discriminated because they make more money. Probably they have been there longer, older. So they're being discriminated. Was there any justification for it? So we should be asking this question. If we are selecting 3 people from a group of 13 people, how many different ways can we do it? Now the question is, if you are laying off people, 3 people, does order really make a difference? Okay, does order make a difference? The answer is no. So we are dealing with combination. So you're picking 3 people from 13 distinct peoples, and how many different ways can this happen? There is no point for me to go over the same thing again and again. So this is just application of this formula. And if you do the calculation, you get 286. So if it were to be completely a random scenario, this is what would happen. So you have 286 different ways of selecting 3 people from a group of 13 people, or selecting 3 managers from a group of 13 managers. Okay, you have 286 different ways. Now, out of these 286, there will be only one group that will have the highest earning 3 managers or top earning 3 managers. So if the company were to really truly do it randomly, they said, oh no, we kind of laid up people randomly, and it happens to be the case that those are the 3 people got laid off or got fired, so it was a random event. There was no bias. So chances of that happening is 1 out of 286, because there are 286 different ways of selecting 3 people, groups of 3 people from 13. Only one group has the top earning 3 managers. So chances of that particular one picking is 1 out of 286, which is about 0.35% or 1/3%. So that's probably a pretty small probability. So my guess is that company probably discriminated, okay? And obviously you guys work, many of you do. The world is not mathematical. When things are bad, if you have bad relationship with your supervisor, you'll get laid off, you'll be let go, okay? That's one of the very important things. When you go to work, make sure that you have people skills. If you don't have it, cultivate it, grow it. You must have to have people skills. People in the real world be successful not because they have really high education. Everybody's got the same level of education. Everybody's got a bachelor's degree or master's degree at the work that you are doing or you'll be doing. Let's say whatever work you're doing. Let's say think of an engineer. We are close to Silicon Valley. Most of these engineers, are almost, I would say, 80 to 90% of these engineers have at least master's degree. So what distinguishes between one engineer who has master's degree versus another engineer who also has master's degree? They can do the same job at the same level of same quality. Is the people skill. Because if 2 people can do the same job at the same level, who is going to get promoted? The one with more people skill, the one with more social skills, the one who is more engaging, more outgoing and reaching out to people. Okay, so this is extremely important quality. Ability to communicate effectively. When I say social skills, it involves many things like ability to communicate effectively, being nice to people, being interactive, being reaching out, being friendly. These are the things. These are things that you don't really learn in a classroom, but you do learn it in a college setting when you make friends and you talk to people and mingle with other people. So it's important. You cannot be shy and quiet and not talking, which I have been personally for a long time, and I still am. I don't think I'm shy, but my friends and my family members, they tell me I'm really shy. That's surprising. How did that happen? But I'm trying to overcome that and try to be more confident in talking to people and be more extrovert as opposed to being introvert. All right, so that takes care of this problem, and this is exactly the same type of problem. I just changed the numbers, so you do it exactly the same way. And then next, these problems I kind of have done them. Okay, this one, how many ways 7 people can sit in 7 different chairs, or 8 people can. How many ways 5 people can sit on 7 different chairs? Order matters. So you'll be doing permutation. So it's going to be 7p5, and 5 people could sit in 7 different chairs where order matters is 2,520 different ways. How many, so this is a tricky one. How many different groups of 5 people are possible that can occupy 7 chairs? Here, the order does not matter because it says different groups of 5. Okay, group of 5 people where order doesn't matter really. So exact same problem. In this case, you'd be doing combination as opposed to permutation. If you do permutation, it's 2,520. If you do not take order into consideration, it just comes down to 20. And that should take care of everything that I wanted to cover for today's lecture. It's a lot of materials, but a lot of more examples, not materials. 2 things to summarize that we have learned is, one is the fundamental counting principle, and another is the permutation combination, actually 3. fundamental counting principle, let's call it fundamental counting principle, then permutation and combination. So these are the three things that we learned about in the second half of the class today. And we have done plenty of examples. And in the first half, we talked about Bayes' theorem, or first third of the class, I guess, Bayes' theorem. So Bayes' theorem, fundamental counting principle, permutation, and combination. So that should be all for the day. And I think since we have a midterm, not this coming Wednesday, today is Wednesday, so not this coming Wednesday, the Wednesday after that. So probably whatever I cover in the midterm, hold on 1 second. When is the midterm? What is today? 24th?
Next week. Exactly next week.
Oh, it's exactly next week. Never mind. So, you know what? I will make your life easier. There is only one topic I'm going to cover for the midterm. In addition to what I have covered, is this binomial distribution, which I will be covering on Monday, and I will probably cover binomial distribution as well as some other stuff, maybe Poisson distribution if time permits, but I will not ask you anything from Poisson distribution, just the binomial distribution, okay? So look at the binomial distribution a little bit ahead of time. I'll cover it on Monday, and that's gonna be all for the midterm. So whatever I covered from the day one of the semester up until Monday, which would be binomial distribution plus more, will be on the midterm, except for anything beyond binomial distribution will not be included in the midterm. So whatever I cover from day one up to binomial distribution would be in the midterm. And I announced the midterm already twice, and you should know the structure and everything. Any question before we end the class for the day? Anybody?
No, you're good.
Okay, thanks. All right. Any other questions? Anybody? One last chance.
Professor, I was a little confused. You said, so the midterm is 1 week from today?
Yeah,
Okay, sounds
on
good.
the third. I'll send an email. I already announced it twice. I'll send a mass email
Okay, sounds good.
to everybody so that you have it too. Okay, thank you so very much. You have a wonderful day and rest of the weekend. Okay, stay safe and healthy. Take care.
Thank you.
Thank you. Thank you. Bye.